Hello, I'm Kyung Min Kim from NAVER Global. I'm leading a team named MLX. In this talk, I will talk about Recommender System 3.0, bias, graph, and causality for the post-deep learning era. At first, I will introduce what is Recommender System 3.0 and positional bias reduction, graph, counterfactual evaluation. Introduction. This figure will describe the major milestone in personal recommender system. Recommender system became popular in the middle of 1990. A classic and simple algorithm is collaborative filtering. In 2006, there was a Netflix prize. At the prize, the winning team used a hybrid model that combines all the models from the other competitors. As of 2010, the computational complexity of models has been getting increased. Many practitioners have used deep learning models to their own problem. Convolutional neural networks, recurrent neural networks have been also used in the recommender system. As of 2016, there was a trial to use causal inference in the recommender system. It tried to convert statistical relationship between models' input and output to causal relationship. As of 2017, there have been many reports which use recommender system with graph. They connect user logs into a log and feed the graph to a recommender system. As far as we know, this is the first time we divide these milestones into 3 pages according to their properties. We call page 1 for the start of the personal recommender system, page 2 for the time when model complexity increased around 2010, page 3 for the time focused on causal relationship. The characteristics of page 1 to 3 are a little bit different. In the page 1, the computational complexity was low and the amount of the data to use was limited. In the page 2, the use of deep learning has increased the computational complexity and the amount of available data to use has also increased with the advance in hardware technology. In the page 3, the ability to interpret the big data has increased. Just using the big data is not enough. The ability to understand the truth in the big data, such as causality, is important. In this page 3, we can manipulate the big data based on deep understanding of how the big data was created. Rather than just feed the data to the model, bias such as exposure position can be removed. Rather than treat each user's log independently, we can connect some logs into a graph. And by converting the correlation between user and click log into a causal relationship, online CTR can be directly optimized in an offline test. In this talk, a use case to explain the technical effect is a recommender system applied in the Line Wallet service. The Line Wallet is being serviced in Japan, Taiwan, and Thailand. In the Line application, the Line Wallet tab displays Line Pay balance, shortcut menu, modules with various content type. Coupon, My Card, points, and 찌라시 are examples of the module. In one module, items of same type are displayed horizontally. Then from now on, I will talk about the recommender system 3.0. At first, I will talk about the removal of positional bias. There are 4 recommender modules in the Line Wallet tab: coupon, My Card, point, 찌라시. We display these 4 modules in the order of the highest click probability for each user. So, how do we calculate the click probability of which module the user will click next? First, we collect the user's past behavioral data. This data specifically contains which module the user clicked or viewed on the line wallet tab, and user group who have similar behavioral patterns. And we feed them to a machine learning model called transformer. This transformer model has been successfully applied in various tasks. For example, translator, chatbot, and even image recognition. With the output of the transformer, the probability of the module the user will click next is calculated. This is a typical example of a supervised learning method, as you know well. Inputs are past behavior and click logs, and output is click probability of the module. With a similar user group, we estimate the behavior of user who have the small number of click logs. It would be nice to finish training the recommendation model like this, but in reality, it needs more work. Because there is a unique problem in recommender system. When we train a recommendation system, we create a dataset from the historical logs. That means we collect behavior logs from user and predict which module to click next. However, there is a bias in click log from line wallet. According to our analysis, 1 in 2 wallet user tend to click the first module regardless of the contents type. As a result, the position of module creates the gap between the rich and the poor. Which means if there are many clicks to the first module, the learning model thinks that the first module is really popular, and it will keep displaying the first module on the top in a high probability. Likewise, if the number of clicks to the last module is small, this module is more likely to be displayed at the bottom. If we do not compensate for such positional advantage, better module order might be missed. So, we create an equation to correct this unexpected phenomenon. In addition to the cross-center loss function, we multiply the CTR of the clicked module. If the number of clicks is relatively small compared to the number of views, we gave a penalty. If the number of clicks is relatively high compared to the number of views, even if the number of clicks is small, we place the module at the top next time. As a result, we found out that this method can increase the CTR more. The removal of positional bias alone results in a CTR increase about 3 times more. So, how much does CTR increase? This figure shows the wallet module CTR. On the graph, you can see CTR increased twice. The one is when we applied our model to 12% of total traffic. The other was when we applied it to 100% traffic. Overall, we can increase CTR 2.5 times more. Now, we have launched the recommendation service in Taiwan and Thailand following Japan. And we are also measuring UUCTR. The UUCTR is the number of unique click user divided by the number of unique view user. After deploying our recommender system, the UUCTR increased by 255% more in Japan, 62% in Thailand, and 37% in Taiwan. During service, we could see the difference between manual placement by human and automatic placement by our recommender system. The figure shows the number of clicks in line wallet module. As you can see, after April 16, the number of clicks decreased dramatically. This is because the shopping module started to be displayed in Line Wallet as of April 16. Because there was no idea on which position we will use to display the shopping module, we decided that in 28% of the total traffic, the shopping module is displayed at the top of the wallet tab. Since the number of clicks keep decreasing, we decide to get down the shopping module from the top. You can see the number of clicks recover after April 22. So from May, we have automatically recommended the shopping module with our recommender system. This is the CTR trend up to the current. We also found out something interesting, that there were the good module and bad module. However, we don't want such polarization. So to eliminate this, we felt that we need a recommendation of items in the module. In Japan, there are outbound items such as coupon and my cards, which should be used outside. The number of users of these outdoor items had increased for several months, but due to coronavirus in worldwide, people don't go outside. Consequently, the number of users has decreased dramatically, as you can see. Chirashi is also one of our outdoor items, but recently the number of users also has decreased. On the other hand, the use of indoor item increased rapidly. The point item is one of the examples. It can be used indoor. If you do a certain task, then you get line points. In this kind of situation, what the recommendation model do is to recommend the point model at the top and Chirashi model at the bottom. In the total traffic, 99% of users get points at the top, 86% of users get Chirashi at the bottom. Therefore, item recommendation should be done together to activate other module. In item recommendation, we use graph to connect relevant logs and represent them as graph. So I'm going to talk about how we use graph in recommender system. LINE Coupon is a current service in Japan. It is a service that provides LINE user with discount coupon for various household items such as shampoo, lotion, and famous food products like McDonald's and Lotteria. More than 500 coupons are served every day, and more than 30 brand products are sold. Before use of recommender system, the most popular coupons were displayed at the first. But from May this year, the recommender system developed by NAVER has been deployed. With this system, we are recommending 10 coupons to approximately 8 million LINE users by considering users' preference. The key to personal recommendation is to display coupon that user will most likely use next time based on their history log. For example, if she likes hamburger, our recommender system will recommend a new hamburger of a similar brand. And if you like bread, our recommender system will recommend another menu he may prefer. Failure to accurately reflect the user's preference can result in a poor user experience and poor usage of the service. Therefore, it is important to develop a recommender system that is precise and capable of catching the latest trend. Recently, many online services are applying a recommender system based on deep learning. Applying deep learning can effectively handle logs from many users and use multimedia data such as image and text of coupons. The basic architecture of a deep learning-based recommender system is shown in the figure. First, user information such as click history, age, gender is used as input and the user's embedding vector is calculated by neural network. Similarly, the coupon's embedding vector can be calculated using information like image and text. Finally, based on this, the model calculates the cosine similarity for the embedding vector of each user and coupon and predict the click probability, that is a CTR. This process is a general form of a deep learning-based recommender system. However, there is one problem with the recommender system that even deep learning has not completely solved. It is a problem called cold start, which means it is difficult to precisely learn the embedding vector for a new user or item, since the existing deep learning-based recommender system independently learns its individual new item or new user with relatively insufficient data tend to be difficult to learn. One of the important solutions developed by Clover is to use graph. And I would like to explain in more detail. First, we define the graph like this. Based on past coupon usage log, our user and item in the log become nodes in a graph. Next, we create edge in the graph if a user uses coupon. We use logs of 70 days. I will show the architecture of the graph-based recommender system. First, multilayer perceptron calculates user and coupon embedding vector by using metadata such as demographic and image. And we don't just use this vector for CTR prediction, and we feed the vector as the initial representation of the graph node. Next, graph neural networks updates the embedding vector by propagating the node representation along the neighborhood in the graph. Finally, the graph neural networks predict CTR based on the cosine similarity of the last updated embedding vector. The graph neural network learns a connection. Existing deep learning method treat each user and item independently, but the graph neural network learns to utilize the information of neighborhood from connection. In other words, it is possible to effectively estimate the preference of neighborhood based on connection. This advantage is useful for cold start problem. Considering real-world recommender system, new user and item appear or disappear every day. The preference of user will also change every day. In this situation, traditional deep learning architecture have to retrain their models on every day to adapt this change. Additionally, it is difficult to learn the meaningful representation for the user or item that have the small number of logs. However, since the graph neural networks can directly utilize the information about connection, embedding vector of user and item can be calculated effectively without updating the parameter of the model. Surprisingly, this graph neural network can catch both CTR and diversity simultaneously. This figure shows the diversity of recommended coupon for both the graph model and non-graph model. The left is a non-graph model and the right is a graph model. We analyze the percentage of each coupon recommended by each model. For each coupon, the higher the popularity over the past 2 weeks, it has the dark red color. As you can see in the figure, in the non-graph model, most of the dark red color are recommended. But in the graph model, you can see that the relatively light colored coupon were mostly recommended. This shows quantitative results. If we use the graph model, novelty and diversity go up, and popularity goes down. Novelty measures how unpopular items are recommended to user. Diversity measure the degree, how much each user get a different coupon. We could confirm that various coupons, including new coupons, have been recommended to users. In this way, if a recommender system recommends a lot of unpopular and new coupons to users, it is easy to think that the performance will decrease. In fact, we could see that CTR has increased. As a result, by developing a recommendation system based on graph neural network, we are able to capture both CTR and diversity simultaneously. Thanks to these good results, the graph neural networks are still being applied to the line coupon service. This is a performance result on cold user. If we use graph model, it gives us CTR increment 9% more than top popular baseline, which is very powerful. However, if we use non-graph model like multi-layer perceptron, the increment is not that high compared to the graph model. Our team continues to work on developing new ideas to better fit to the real-world problem beyond just applying existing algorithm. If you are curious about detailed information for the graph model, you can read the paper here. Finally, I will talk about counterfactual evaluation and our future development plan. In the process of developing a recommender system, a recommendation model is trained from past log of user. And among various recommendation models, a model to be deployed online is selected by evaluation such as precision and recall. Then, how did we know that the new model will work well in online? But the important thing is that applying metric like precision and recall are different with CTR, which is what we really want to measure in business. They are very different. In this case, counterfactual evaluation plays an important role. Counterfactual evaluation means making an evaluation that goes against fact. It helps you select model that will have high CTR in an offline test. There are several methods of counterfactual evaluation. There are many families of inverse propensity score methods, and there is another algorithm such as CAP. The table shows the offline evaluation method that correlate strongly with CTR. The value in the table are the model ranking on each evaluation method. The higher the correlation between the ranking of CTR and the ranking of counterfactual evaluation, the better. In the table, you can see that about 3 evaluation methods highly correlate with CTR. Our team will combine this counterfactual method with AutoML. After setting the counterfactual evaluation as an optimization value, we expect to be able to further improve the value of online CTR by tuning various models using AutoML. In addition, using AutoML will greatly reduce the management cost of the recommender system. That is all I have prepared for this talk. The important point in recommender system 3.0 is that data can be manipulated based on the ability to interpret big data. For example, positional bias removal, graph construction, and counterfactual evaluation. We will make more interesting results and see you next time. Thank you for listening.